This will be the first in a series of 5 videos on cardiac electrophysiology, looking at action potentials and related topics in the heart. This first one's going to focus on contractile muscle action potentials, so how APs occur in the muscle cells of the heart that actually do the pumping. I want to begin this with a brief review of action potentials as they occur in neuromuscular tissues, so in skeletal muscle or in neurons, because my experience over the years is if you know neural action potential well, cardiac AP is just a slight modification of it. So as different as it looks, you can learn cardiac AP much more effectively if you know neural AP first. So with that in mind, let's take a look at our graph. Here we have on the x-axis time in milliseconds, and on the y-axis we have voltage. And I'm going to mark a few things on the y-axis here. There's 0 millivolts, there's resting membrane potential, and there's threshold. I don't personally care in my classes that students know these specific values for RMP and threshold because there's some variation from tissue to tissue, and really it's more the principle of what is RMP, what is threshold. That's what matters the most. So I'm not going to be putting values for those on here, and I don't personally care about them. Let's start with our neural AP, or our skeletal muscle AP, whose membrane is at resting membrane potential. It experiences a stimulus that produces a small graded depolarization, but one that's big enough that reaches threshold. And at threshold, the depolarization phase of the AP begins as sodium voltage gates open. Sodium flows rapidly into the cell, producing large depolarization and slight reversal of membrane potential. As the sodium voltage gates close, potassium voltage gated channels become fully open. Potassium flows out of the cell and moves the membrane back towards resting potential. But because those potassium voltage gates are slow to open, they're also slow to close. And as a result, we undershoot resting membrane potential slightly in what's called the hyperpolarization phase. And eventually, when the potassium voltage gates close, with some assistance from the sodium-potassium exchange pumps, we return to resting potential. That's an action potential as you should remember it from Anatomy and Physiology 1. Now, let's take a look at a cardiac contractile action potential. Now, keep in mind, I'm going to be tracing this on top of this graph with the neural AP in the background. I'm not going to be doing this perfectly to scale because my goal here isn't to show you the scaled differences between these, but to show you the similarities and how the differences are easy to understand if you think about the similarities. So what I'm about to put on here is absolutely not to scale. Keep that in mind. So our cardiac cells are at resting potential. They experience a stimulation, a graded depolarization that pushes them to threshold, just as we've seen with the neuron, just as we see with the skeletal muscle. At threshold, sodium voltage gates open and the influx of sodium rapidly depolarizes the cell. So far, it's all the same. At this point, the sodium voltage gates close and the potassium voltage gates begin to open, which starts to push the membrane into its repolarization phase. But at the same time the potassium voltage gated channels are opening, so are calcium voltage gated channels, which allows calcium to diffuse into the cell. Now, keep in mind, calcium concentrated outside the cell is there in a much lower concentration than sodium is, but it's more concentrated in the extracellular fluid, so it is going to diffuse in. It's a positively charged ion moving into the cell, so if you have positively charged ions moving into and out of the cell at the same time, calcium in and potassium out, the result is what we call the plateau, where where membrane potential stays relatively constant for an extended period of time. Now, I'm not showing this plateau to full scale here. The actual plateau is going to last for several hundred milliseconds. Remember, the neural action potential that's already drawn in the background lasts only about 2 milliseconds. So I'm really not showing the full scale of this plateau here just as a convenience. Eventually, the calcium voltage gates close, and with the potassium voltage gates fully open, the outflux of potassium pushes the membrane back towards resting potential, and eventually when the potassium voltage gates close, we return to resting potential. I want you to notice this is very similar to what we saw in the skeletal muscle action potential. The real difference is the timing of the potassium channels becoming fully open and the fact that calcium channels are open at the same time. And so that skeletal muscle action potential or neural action potential lasts about 2 milliseconds. The cardiac contractile action potential lasts in the order of 400 to 500 milliseconds. It's much, much longer. To summarize, differences between contractile cardiac APs and skeletal muscle APs. Contractile cardiac APs last longer due to the plateau during repolarization. The plateau is a product of calcium ions entering the cell as potassium ions are leaving. And just as an extra side note that I didn't mention earlier, that calcium that moves in during the plateau also binds with troponin to facilitate muscle contraction. And this is something very different than what you saw with skeletal muscle. So actual contraction and the intensity of the contraction in cardiac muscle is a function of the calcium that enters the cell during the plateau phase of the AP. So it's not just about changing the timing of the AP, it also has consequences for the contraction process, and therefore pharmacological interventions that affect heart function, you got to pay attention to how they work when we talk about that down the line.